Hi, I'm Jeff Lukas with the Western Water Assessment Program at the University of Colorado Boulder. Thanks for joining us. The availability of water in the West under natural conditions is incredibly variable over space and time. Water is very unevenly distributed from one place to another and fluctuates from season to season, from year to year, and decade to decade. When those fluctuations are on the dry side and are long-lasting, we have drought. Fluctuations on the wet side are usually more welcome unless there's too much of a good thing, and then flooding results. In learning about the development of water resources in the West, you've seen that the legal and institutional arrangements, as well as the physical infrastructure, were set up in large part to deal with this natural variability. In this lecture, we'll look at the underlying mechanisms that drive this variability in water resources, the main climate processes that affect the region, and the characteristics of the Western landscape that interact with those processes. As soon as precipitation, rain, snow, hail, reaches the ground, it is liable to be taken right back up into the atmosphere. The atmosphere is like a sponge that gets periodically wrung out and then is thirsty again. The resulting pull of moisture from soils, from crops and other vegetation, and from the snowpack is called evapotranspiration, or ET. Only in those places where annual precipitation, on average, is greater than evapotranspiration consistently do we get surface runoff, water flowing into streams and rivers. Let's look at the processes that produce precipitation in the West. At the latitudes of the western US, the upper level winds flow from west to east. In fact, the largest moisture source on Earth, the Pacific Ocean, is just upwind of the West. So in the fall, winter, and spring, every 3 to 10 days, a low pressure system, a storm, will come onto the west coast of the US or Canada, loaded with Pacific moisture, and follow a usually curving track across the region, following the jet stream, the core of the strongest upper level winds. It is these cold season storms that supply most of the water to the western US. As these storms track through the region, the moisture embedded in them runs headlong into the West's mountain ranges, starting with the Coast Ranges, the Sierra Nevada and Cascades, and then the Rocky Mountains. These ranges tend to be oriented north-south as a result of the geological forces that have acted upon this region over time. The water vapor is forced upslope, what we call orographic lift. Some of it cools, condenses, and falls. The higher up on a mountain range, the more precipitation tends to fall, with the maximum usually at the crest of the range. And the higher the elevation, the more of the precipitation that falls is snow instead of rain. And because the mountains are colder and cloudier than the lower elevations, evapotranspiration, that pull of moisture back into the atmosphere, is less as well, which tilts the mountains more towards a positive water balance and thus more runoff. And then as the flow descends the other side, usually the east side of the mountains, the downsloping air warms up and can't easily release its remaining moisture, creating a rain shadow that extends dozens or even hundreds of miles downwind. In the late spring and summer, the strong westerly winds weaken and shift northwards. This allows for moisture from the Gulf of California and the Gulf of Mexico to move northward into the west. Where the intense summer heating of the land surface causes air to rise, convection, and form thunderstorms. This is what we call the North American monsoon, which is strongest in Arizona and New Mexico, but extends into Utah and Colorado as well. These summer rains are not as important for water supply as the winter snowstorms, but they do strongly influence the demand for water in crops and cities. So you end up with a pattern of wet mountains or islands of moisture and dry basins and valleys in between. The mountains, having both high precipitation and low evapotranspiration, produce virtually all of the West's runoff, even though they cover less than 10% of the land area. The lower, drier areas have high ET and produce only a little, if any, runoff. They are largely dependent on mountain watersheds that may be tens or hundreds of miles away. Because the precipitation in the mountain headwaters falls mainly as snow, the western US has what we call a snowmelt-dominated hydrology. The snow that falls from roughly October through May is stored in the snowpack and then rapidly melts and runs off in the early summer. The snowpack is like a reservoir in that it stores water from when it falls until it is more needed, but unlike a man-made reservoir, it cannot store water from year to year. So let's turn now to the variability in precipitation and runoff over time, from year to year and decade to decade. In most locations in the West, there is a huge difference by a factor of 2 to 5 between the wettest and driest years, with the largest fluctuations in the Southwest. These fluctuations in annual precipitation drive very similar looking fluctuations in annual runoff. But because the translation of precipitation to runoff involves the large influence of evapotranspiration, the range for annual runoff is even larger than that for precipitation. In the mountains of the West, most of the annual precipitation, and so most of the runoff, comes from a relatively small number of storms during the fall, winter, and spring, maybe a dozen events or fewer. So the average north-south position of the westerly jet stream and the prevailing storm track in a given year can determine whether it ends up wet or dry. Many of the undulations and shifts in the jet stream are essentially random, coming from the chaotic fluid motions of the atmosphere. But the enormous heat storage capacity and the slow movement of the oceans leads to coherent patterns or modes of variability that play out over years to decades, influencing the weather and climate of the West in a partly predictable manner. The most important of these modes is ENSO, El Niño Southern Oscillation, which is a phenomenon in the tropical Pacific that involves changes in both ocean temperatures and the prevailing winds over a roughly 2 to 7 year cycle. The warm phase of ENSO is called El Niño, and the cold phase, La Niña. The tropical Pacific is the main heat engine of the planet, absorbing and transferring enormous amounts of solar energy north and south into the mid-latitudes. This tropical influence on the atmosphere's circulation varies over time, in part depending on the phase of ENSO. During El Niño, the jet stream and the storm tracks over the West tend to be in a more southerly position, favoring most of California, Nevada, New Mexico, and portions of Utah and Colorado, while the Pacific Northwest is usually drier than normal. During La Niña, the cool phase, the storm tracks tend to be in a more northerly position, which tends to favor the Pacific Northwest and the Northern Rockies, while the Southwest is usually drier than normal. Historically, sustained droughts in the interior western US have been associated with persistent La Niña conditions because of the large area with dry tendencies during the La Niña phase. Because El Niño and La Niña conditions usually persist for several months or longer, once we are in one phase or another, we have some skill in predicting whether parts of the West will be wet or dry looking forward a season or two. There are also longer-term modes of climate variability that affect the West, where the ocean varies on timescales of several years to decades. The Pacific Decadal Oscillation, or PDO, is a measure of ocean temperatures in the North Pacific Ocean. Like ENSO, the warm phase of PDO is associated with wetter conditions in the West, and the cold phase with higher odds for drought. The Atlantic Multidecadal Oscillation, or AMO, reflects slow changes in the North Atlantic Ocean. The AMO also appears to influence conditions in the West, especially the moisture in the spring and summer coming from the Gulf of Mexico. Since about 2000, there has been an apparent shift to overall drier conditions in the West, with below normal precipitation and below normal runoff in most years. The Upper Colorado River Basin, for example, has experienced the lowest 15-year period of annual runoff in the past century. And most of the area of the West was affected by moderate to extreme drought in 2001 through 2004, 2007 through 2009, and 2012 through 2014, with only a few truly wet years in between. Can we explain this dry start to the 21st century in the West by looking to the modes of variability like ENSO and the PDO? If we look at ENSO, since 2000 there have been no strong El Nino events and a tendency towards La Nina conditions. There has also been a negative or cold phase PDO and a positive or warm phase AMO. These would all tend to tilt the West towards dry conditions. So in general, the low precipitation in the West from the last decade plus is consistent with what we would expect from these various nudges on the storm tracks, plus the usual chaotic behavior of the climate system. Also, the precipitation deficits in the West since 2000 are not outside the range of variability of the past century. However, alongside these continuing oscillations of the climate system, there have been other changes. The Earth has warmed, especially since 1950, and most of that warming has been attributed by climate scientists to human causes, mainly the unprecedented increase in greenhouse gases, including carbon dioxide. This global warming is reflected in recent warming in the West, where annual temperatures have increased by around 2 degrees Fahrenheit in the past 30 years. This regional warming has also been mainly attributed to human causes. So with respect to recent trends in water resources in the West, the natural variability in precipitation has interacted with warming temperatures, and this warming has a human-caused component. The warming temperatures seen in the last few decades have increased the size of the atmospheric sponge, thus tending to increase evapotranspiration from soils, from vegetation, from the snow. Given the same amount of precipitation, we would expect a decrease in runoff under a warming climate. And in fact, there are indications that runoff in the past decade across the West has been lower than what we would expect based on historical relationships from the precipitation that has fallen. But there's so much variability in runoff from year to year that it's hard to tease out a clear signal from just the warming so far. To summarize, the interactions of climate processes with the complex topography of the West leads to large variations in water supply and water demand across the region and also over time. The modern settlement and development of the West has hinged on efforts, mostly successful, to even out the variability in water resources driven by climate. Human-caused climate change is expected to cause major shifts in water availability and water use in the West, and those will be explored in a later lecture. As these shifts play out, the high natural variability in water over space and time in the West will continue. The future of water in the West will depend on our ability to adapt to both our highly variable climate and the changes that come in the future. Well, thanks for watching, and we'll see you in a later lecture.